this is Pre-Algebra Lesson 3-10, and this lesson is going to give you a nice break in that it's not a math-heavy lesson, but you are going to need to do some serious thinking in this lesson. So we're going to be categorizing numbers, and it's pretty cool. All right, if you will look with me on page 156 at the top, and I'm going to read to you. Biologists classify animals based on shared characteristics. The gray lesser mouse lemur is an animal, a mammal, a primate, and a lemur. Look at the diagram that they've drawn for you right below that, and you see the picture of the lesser mouse, which is tiny, weighs only 2 to 3 ounces, and lives 10 to 15 years. Isn't that crazy? That's amazing to me that an animal that tiny would have such a long lifespan. All right, so what they're showing you in that diagram is that animals are your big overriding category. And then the further into that diagram we get, the more specific we get. So mammals are a type of animal. Primates are a type of mammal, which are a type of animal. And lemurs are a type of primate, which is a type of mammal, which is a type of animal. And they didn't go on. They could have gone one box smaller inside of the lemurs and put the lesser mouse, because it's the lesser mouse lemur. So they could have even made that a little more specific. But we're going to be doing the exact same thing, but with numbers. So I'm going to be reading to you for a minute. You read along with me in your book. You already know that some numbers can be classified as whole numbers, some as integers, some as rational numbers. So let's talk about those for just a minute. This is going to be important. I would like for you to get this down on paper because it'll help you in your homework to be able to keep looking back at this, at these definitions. So just pause your video for a minute and write down all of these, and be careful to write them the way that I've written them in this order. And I'm going to keep talking, but you'll come right back to what I'm saying as soon as you're done writing it down. So let's go over those. We have whole numbers. Whole numbers are not fractions, and they are not negative. We start with 0 and we count our way up. Then we move to integers. Integers are whole numbers in a way in that they're not fractions, but we add something this time. We add negative numbers. So integers are positive and negative whole numbers. Remember up here, the true whole numbers were not negative. All right, let's go down to the next one. Rational numbers we have studied. They're numbers that can be written as fractions or as the quotient of a fraction. And they are also decimals that end or repeat, but not decimal numbers that keep on going forever without repeating. We call those irrational numbers. Decimals that do not end and do not repeat. That would be like 7.2, 3, 4, 5, 6, 8, 2, 1, on and on and on and on and on with different numbers and without repetition. Okay, and the last one that we're going to look at is real numbers. Real numbers are all rational and all irrational numbers. So real numbers are kind of like the animals in the first diagram. They are the overriding category, and these others fit into real numbers. And that's what we're going to be looking at today, is classifying numbers. All right, let's see. Let's give a couple of examples here. An example of an integer would be 2. It's a positive whole number, but it would also be -4. Let's look at rational numbers, numbers that can be written as fractions, like 4/5, or 3 4/5, or 6 divided by 9, 6/9, because that's going to be a repeating number, or 2/3, which is a repeating decimal number. And they give the example of the square root of 1.44, whose answer is 1.2, or the square root of 16, whose answer is 4. All right, let's look. Well, actually, that would be. That one is not a decimal that we're looking at here that ends or repeats. That's why they gave the decimal square root number. All right, now let's look at irrational numbers. I think we did that. Decimals that do not end and do not repeat, and that's what I gave you an example of, the number that goes on and on and on with no repetition. And then we come back to our real numbers, which includes all of these and all of these and everything above. So look at the diagram that they've shown you. They have broken it down. It's a diagram similar to the top with the animals, but this time they've broken it into the rational on one side and the irrational on the other. So rational numbers are what encompass the integers and the whole numbers. Irrational are in their own category, but they do fall under real numbers. All right. So if you read, you can see that irrational numbers are the decimal numbers that do not repeat, and they give you the example of the square root of 2, and you see what that looks like. Now, an important note here, actually two important notes. If we are using a calculator to find the square root of 2, it sometimes may look like it terminates because calculators can only give you so many numbers, and different calculators are going to give you different numbers of decimal numbers or numbers after the decimal. So in this case, they're showing you that the square root of 2 goes on and on and on, whereas your calculator may look like it terminates. So be careful about that. And one of the things that they tell you, which is the other important part, is if a whole number is not a perfect square, then its square root is an irrational number. So what that's telling you is if it is like the square root of 10 that we looked at in the last lesson, 10 is not a perfect square. It does not have a whole number that's multiplied by itself to get 10. So we consider it an irrational number because it goes on and on and on in a decimal if you do it on a calculator. Okay, so now let's look at classifying numbers. Let's start, and I'm going to turn my camera just a little bit now that you've had a chance to write those down. And we're going to look at the square root of 3. All right, we know that the square root of 3 is not a perfect square. It doesn't have a number that multiplies by a whole number that multiplies by itself to equal 3. So it can't be rational, it's going to be irrational, because the book just told us that if a number is not a perfect square, then its square root is going to be irrational. So we're going to write as our answer in homework, irrational, and you can abbreviate if you would like to. We also, though, know, looking at our diagram, that irrational numbers fall under the category of real numbers, so it's irrational and it's real. Remember, real numbers, if we go back to our definition right here, real numbers are all rational and irrational numbers. So that's why we categorize this one as irrational, but then the bigger category that it fits in is real. All right, let's look at another one. Negative 56.85. Negative 56.85. This is a decimal number that terminates. It does not keep going. So that's going to make it a rational number. So we're going to say rational. I'm going to just abbreviate it this way. You can abbreviate it however you would like. And we know that rational numbers are also real numbers because real numbers are all rational and irrational numbers. But is it a whole number? No, because it's a decimal. Is it an integer? No, because integers are negative and positive whole numbers. So it can't be a fraction or a decimal. All right, let's look at another one. The square root of 9 over 3. The square root of 9 over 3. You're going to need to do a little bit of math on this one because in order to think through it, you've got to think through that square root of 9. Well, the square root of 9 is 3. So this is really 3 over 3, and its final answer is 1. So what are we going to call that? Is it a whole number? Yes. So we're going to write whole. What else is it? Is it a positive or negative whole number? Yes. So it's an integer because 1 is a whole number. It is positive or negative. Is it rational? Yes, it can be written as a fraction like that and still equal 1. So it's rational, and I'm going to write R-T-N-L, and I'm making sure you can see all of this. And is it irrational? No, it's not a decimal that never ends. Is it real? Yes, because all of these categories fall under real. So we will say real. Okay, now let's move to the top of the next page, the top of page 157 for just a minute, and we're going to talk about two things here, two important notes. The square root of a negative number is not a real number. So let me give you an example of that. The square root of negative, let's say, negative 100. It could be negative anything. We do not consider that a real number. You're going to learn about that in a few years. Those are super fun to work with. We call them imaginary numbers, but we're not anywhere close to learning about those right now. So if it is the square root of a negative number, and by that I mean the negative is on the inside of the radical sign or the square root sign, you can use those two words interchangeably, then we do not consider it to be a real number. And that would be your answer, not a real number. Also, if your fraction has a denominator with 0, we consider it to be undefined, so it is not a real number either. All right, let's look at some more examples. I'm going to erase the examples that we've done, and I'm going to check my time really quickly and make sure that we're doing okay. Yes, we've got a little bit more. So the square root of 10. Let's talk about whether these are rational, irrational, or not a real number. Those are the options that they gave us in this example. So we don't have to go through the whole list like we did before. This time, we're limited to these categories: rational, irrational, or not a real number. All right, the square root of 10. Well, remember the book told us that anytime we have the square root of a non-perfect square, then it's going to be an irrational number. It's going to be a number that's decimal places do not terminate or repeat. So we would say irrational, and I'll abbreviate it right there. Okay, let's see, I feel like I was going to tell you something else about that. Oh, just remember, I try to keep saying this, a perfect square is when you have a number that multiplies by itself perfectly to get that answer. So 10 does not have anything that multiplies by itself perfectly to get that answer, so it's not a perfect square. Okay, let's look at the next example. 3 divided by 0. The book just told us that anything with 0 in the denominator is considered undefined. It is not a real number. So that's all we would say is not a real number. And the next example, oh, that sign means number. I'm sure you'll know that already. The next example is the square root of 1/4. Now, we haven't talked about this yet. Let's look at it. When we have a square root sign that involves the whole fraction, we simply can put the square root over the top, the numerator, and the square root or the radical sign over the bottom, which is the denominator. And then we treat them independently. We find the square root of 1, which is 1. It's a perfect square. 1 times 1 equals 1. And the square root of 4, which is another perfect square because 2 times 2 equals 4. And the answer to this problem is 1/2. Would this be rational or irrational? It's rational. It can be written as a fraction, and if you divided that fraction out as a decimal, it would be 0.5, which terminates or ends. So for this one, we would say rational. Okay, last one, -17, and I want to make sure you can see this in the camera window. Yeah, you're good. All right, remember, when we have a negative square root, meaning the negative is inside the square root sign, it is an imaginary number. And this, we just call it not a real number. So that's what you would write, not a real number. All right, that is it for that. We have one last thing to look at, and that is applying the density property. All right, read along in your book in the middle of the page, and I'm going to have to go super fast on this. The density property of real numbers states that between any two real numbers is another real number. This property is also true for rational numbers, but not for whole numbers or integers. For instance, there is no integer between -2 and -3. The reason for that is that integers are whole numbers that are positive and negative, and there is no whole number that's negative between -2 and -3. Those would have to be fractions or decimals. All right, I am completely going to run out of time. I'm going to stop this video and we'll finish it in just a very few minutes in a third video.